Again, good morning. Today we're going to talk about Chapter 6, begin Chapter 6, which is entitled Rational Expressions and Equations in our text. And the first section of Chapter 6 is entitled Rational Functions and Simplifying Rational Expressions. Well, what's a rational expression? Before we talk about rational expressions, let's talk about rational numbers. You've heard the expression rational numbers many times in your mathematical careers, I suppose. And the big clue here is ratio. Ratio is embedded in the word rational or rational. And rational numbers, well, examples of rational numbers are minus 1/2. That's a rational number. 3/4 is a rational number. 7 is a rational number because we can write it as 7/1. 0 is a rational number because we can write it as 0 over anything. All right, the idea here is rational numbers are ratios of integers. Integers are just whole numbers and they're negatives. And that's a fancy word for fractions. Right? Rational numbers are nothing more than fractions. All right? The concept extends to rational expressions. What is a rational expression? Well, again, the word ratio is embedded in the word rational. Rational expressions are nothing more than ratios of polynomials. Some people call them algebraic fractions. Well, for example, 3x squared over x minus 7 is a rational expression. It's a ratio of expressions of a variable in the form of polynomials. And some polynomials are simple, some polynomials are complicated. X squared plus 2x plus 3 over x minus 1. That is a rational expression, ratio of polynomials. Remember, a polynomial is a sum of monomials, so all monomials are polynomials. So 2 over x squared is indeed a rational expression, etc. We'll be dealing with lots of rational expressions today. What is a rational function? Well, in simplest terms, a rational function is really a function assignment based on a rational expression. So, for example, if we say f of x is a function whose formula is defined by a ratio of polynomials, we call that a rational function. And again, we usually use the letters f, g, and h to assign functions. So g of x, you make up anything you want, I suppose. X minus 3 over 2 minus x, that is a rational function. A function whose formula is defined by a rational expression. Alright, definitions are down, so we're going to get right to some examples. Simplifying rational expressions. Let me give you the simplest possible rational expression. Well, constants are polynomials also, as we know, so we can simplify this rational expression. Of course, we know we can break it down and spot the common factors. Anytime you see common factors over a fraction bar, you can cancel them out, and of course 6/8 equals 3/4 in lowest terms. How about if we simplify something a little more complicated? Let's say we've got 12a to the 4th b squared divided by 20 ab to the fourth. Well, of course, we've done this before in our previous chapters. Basically, we identify the common factors and cancel them out according to our cancellation laws. 12 over 20 reduces to 3 over 5. We see a common factor of 4 in both 12 and 20. A to the fourth power over a. Well, 1 power of a in the denominator cancels out all but 3 powers of a in the numerator. And of course, b squared over b to the fourth power. That will simplify with a residue of 2 factors of b in the denominator. Alright, so how do we simplify rational expressions? Basically, we spot common factors and cancel them out just like we did in the previous chapter. Let's do another. Simplify. Simplify the following rational expression. Let's say 28 x to the fourth power. Here our denominator is going to contain a sum, or difference, 7x to the fifth minus 14x to the fourth. Now let me illustrate a common error that happens, and I'll put it in hot pink so you'll not make this mistake. A plus b over a, you cannot make this cancellation. You cannot cancel out terms of a sum over a fraction bar, and it's a common mistake students sometimes make. But if I've got a times b over a, if I've got common factors over a fraction bar, yes, I can cancel those out. Okay, so some students might tend to cancel out these x to the fourth powers here, but beware, you cannot cancel those out. You've got to have common factors, meaning elements of a product, over a fraction bar. So let me say this no. I'm going to put that in pink. No. Okay? Alright, let me rewrite that. Now that I've talked about that common error, let me rewrite this example. Simplify. Back to yellow. 28 x to the fourth divided by 7x to the fifth minus 14 x to the fourth. Alright, since we can only cancel out common factors over a fraction bar, you'll want to factor completely the numerator and denominator. Well, the numerator is already factored. It's just a monomial, can't really factor it. Downstairs we can see a common factor of 7x to the fourth. Alright, so if I factor that denominator first, 7x to the fourth leaves me an x minus 2 inside these parentheses. And now these are factors. That x to the fourth power is a common factor, top and bottom. Alright, 7 cancels into 28 4 times, leaves a factor of 4 in the numerator. The x to the fourth powers, yes, those are common factors across a fraction bar now. And the x minus 2 is left in the denominator. Okay? So your final answer here is 4 over x minus 2. Alright, please note, you cannot cancel this 2 into the 4. Let me illustrate that error again. A lot of students will get this far, they'll have the correct answer, and they'll then do something like this. 2 goes into 4 twice, and say something like x 2 over x. No. You cannot cancel out terms of a sum. You can only cancel factors of a product across a fraction bar. Okay? Alright. New screen. Another example. Simplify. Simplify the following rational expression. So we've got x squared minus 6x plus 9 in the numerator divided by 6x minus 18 in denominator. So of course we've got sums and differences in numerator and denominator, and we can't do any cancellation until we establish factors of a product. So clearly I've got to factor completely the numerator and denominator. Alright, the top polynomial is what we call a perfect square trinomial. It's a square of a binomial, as we've seen in previous chapter. So it factors as x minus 3 times x minus 3. Downstairs, of course, I can factor out a 6. I've got 6 times x minus 3. And now, I've got products of factors in numerator denominator. Now I've got a common factor of x minus 3. So I'll cancel out the expression x minus 3 top and bottom. And my final answer is x minus 3 over 6. No, you cannot cancel out the 3 with the 6, as we've talked about a couple of times already. Alright, so once you factor these expressions properly in numerator and denominator, it's really not too bad. Of course, some are more complicated than others. Simplify. Take a trinomial in the numerator divided by a trinomial in the denominator. Make sure I copy this right. You go down here. Alright, of course we've got sums and differences of monomials in both numerator and denominator, and you can't cancel out sums, pieces of sums and differences. You've got to identify common factors. So I'll factor completely numerator and denominator. And I think the numerator will factor as, let's see, 2b and b in the first slots. If I've got 5 and 3, I think I see it, 5 and 3. If I take a plus 10b and minus 3b, I think that factors properly. And downstairs, 2b and b in the first slots. Both signs are positive here, which means both signs are going to be positive here. 2b, let's see, 15, 5, and 3. Oh, yes. Right. 2b plus 3 times b plus 5 in the denominator. Right. Now I've completely factored, and I see a common factor of b plus 5, top and bottom. So with that cancellation, I'll write 2b minus 3 divided by 2b plus 3, and that's my final answer. All right, notice the numerator polynomial is prime, the denominator polynomial is prime. There are no common factors at this point, so that's my final answer. No, you can't cancel out the 2b's, and you can't cancel out the 3's, okay? Alright, I'm going to identify what I'm going to call a building block for further problems in this section, in this chapter. Simplify. A minus b over b minus a. Alright, no, you can't cancel out the b's, you can't cancel out the a's because they're not factors. Right? They're terms of sums or differences. Alright, what I can do, though, is notice that the denominator is really the opposite of the numerator. Let me show you. If I factor out a minus 1 from the denominator, you can always factor out a negative 1 by changing all the signs. I now see I've got a common factor of a minus b across numerator and denominator, right? So I can cancel those out. I'm left with 1 over negative 1, which is, of course, negative 1. So the idea here is if you can identify numerator and denominator as being opposites of each other, you can instantly reduce this to the number negative 1. Okay, and we're going to use that in many problems in this section. A minus b over b minus a always reduces to negative 1. Simplify. Something a little tougher. 3x squared minus 10xy minus 8y squared divided by 4y squared minus xy. Alright, don't go canceling out first. Factor first. You can only cancel out common factors across a fraction bar. Alright, well, my numerator polynomial, the first term is 3x squared, a multiple of x squared. The last term is a multiple of y squared, and the middle term is a multiple of xy. So I think I can put 3x and x in the first slots. Of course, my last terms are going to be multiples of y. Let's see, they're going to have opposite signs. Let's see, I'm going to try 4y and 2y. And I think 2y times 4y is, of course, 8y squared. So I think I can play with the signs. If I get a, let's see, a minus 4y will give me an outer product of negative 12xy, and then the inner product would then be plus, if there's a plus sign here, plus 2xy times x would be plus 2xy. And indeed I get the correct inner and outer sum. Alright, so that factors the numerator. Denominator is a little easier. I can factor out a y, of course. Y times 4 minus x. Oh, 4y. Whoops. Y times 4y minus x. Factoring out a y from the denominator. Alright, please convince yourselves that x minus 4y and 4y minus x are indeed opposites. Okay, they are of the form a minus b over b minus a. So I can cancel these out, and in their wake leaves a factor of minus 1. And you can absorb that negative 1 in either the numerator or denominator. Alright, so that would be a wonderful final answer. I think our textbook might write something like this. That is also an equivalent and wonderful answer. If you want to distribute that negative 1 through the numerator, 3 minus 3x minus 2y over y, that's also a fine answer. And I can even absorb that negative sign in the denominator. I could say 3x plus 2y over negative y. And I think our textbook would sit this negative sign outside the fraction operation. Alright, so any of these four answers are equivalent, and they're all fine. Just alternate ways of how to embrace that negative factor in that final rational expression. Simplify. D squared minus 16c squared over 4c minus d. Alright, we want to completely factor first. The denominator is prime, is it not? So I'm just going to rewrite it in my first step. The numerator is a difference of squares pattern, as we saw in one of the last sections of last chapter. So I'm going to claim that's d plus 4c times d minus 4c, according to my difference of squares pattern. And again, notice d minus 4c and 4c minus d, when you switch the order of subtraction, it's equivalent to negating. So d minus 4c and 4c minus d are indeed opposites. They are of the form a minus b over b minus a. Please convince yourselves of that. So when I make that cancellation, I'll throw in a factor of minus 1 in its stead. Alright, so I'll say I've got a minus 1 times d plus 4c in my numerator over, well, if you cancel out the 4c minus d in the denominator, the invisible divisor of 1 appears. Of course, it's redundant to divide by 1. So I'll claim my final answer is negative d plus 4c, and that's a fine answer. Or if you want to go ahead and multiply it through, the negative 1 through, I get minus d minus 4c. I think our textbook would probably cite this as a final answer, but either of these answers are equivalent, of course, and wonderful answers. Okay? Alright. Let's do something a little nastier. Simplify. A cubed minus ab squared, binomial of degree 3. Downstairs I've got ab squared minus 4a squared b plus 3a cubed. Alright, so again, we can't make any cancellations until we establish factors of products. So I'm going to, of course, factor the numerator completely. Well, the first thing I see is a GCF in my numerator. I can write that equivalently as a times a squared minus b squared. And of course, I can factor that again. And downstairs, well, I can also factor out an a. And I'm left with b squared minus 4ab plus 3a. And of course, those polynomials in parentheses in both numerator and denominator can be factored again. So be sure to factor completely before you start hacking out common factors. The numerator contains a factor that's a difference of squares. So of course I can factor that again as a times a plus b times a minus b according to our difference of squares pattern. Downstairs, a little tougher, I think this trinomial in the denominator, in parentheses in the denominator, will factor again. If I put b's in the first slots, and let's see, I'll put a 3a and a in the last slots, the outer product here would be ab, the inner product here would be 3ab, and I think I can play around with the signs to get the inner and outer sum to add up to a negative 4ab. Clearly both these signs are going to be negative. And then I've got b squared minus ab minus 3ab and plus 3a squared. Oops, please forgive me, I forgot to write 3a squared here. Please note that mistake. Let's check it again. Okay, I'm checking to make sure this product equals this trinomial here. So check it again. B times b is b squared. That's fine. The outer product minus ab. The inner product minus 3ab. That indeed adds up to a negative 4ab. And the last product, negative 3a times negative a, is of course plus 3a squared. So I've successfully completely factored each numerator and denominator. And now I look for common factors. Alright, a over a cancels out. Common factors of a. A minus b over b minus a, again, will cancel out and leave a factor of negative 1 in its wake. So finally I'm left with negative 1 times a plus b in my numerator divided by b minus 3a in the denominator. And that's a fine answer. Again, you could multiply that numerator through by negative 1 and get this equivalent answer. I could even absorb that negative sign in the denominator, multiplying top and bottom by negative 1, and get a plus b over, well, I could write it as the opposite of b minus 3a is 3a minus b. Right? Please convince yourselves that these are all equivalent answers, depending on how you want to absorb that -1 factor. I think our book would probably pick this one. They're always looking to save ink when they're printing textbooks. Alright, one more. I believe this is the last one in the homework list. Let me get a fresh screen here. Simplify. T cubed minus 5t squared plus 6t divided by 9t minus t cubed. Alright, so upstairs I've got a trinomial, downstairs I've got a binomial. Before I start simplifying, I've got to factor completely. First thing I'll see in the numerator is a GCF of t. And it looks like that trinomial in the numerator that's in parentheses will factor again. I'll pause to do that. Downstairs I see a GCF of t. Alright. So I will factor again. The numerator polynomial in parentheses will factor as t, let's see, 6 and 1. I think it'll do it, and a -6 and a +1. So t squared minus 5t plus 6 factors as, no, that's not correct, because look, +1 times -6 gives me a -6, and I need a +6 here. So let me try again. Again, factoring trinomials is a trial and error process. I think I see it here, -3 and -2 will do it, right? Let me check it. The first product is t squared, that's fine. The outer and inner product adds up to a -5t, and now -3 times -2, the last product is of course +6. Alright, let me clean this up. So I've completely factored the numerator into prime factors. Downstairs, well, I've got a factor of t sitting out here, and of course 9 minus t squared factors as a difference of squares. I'll call it 3 plus t times 3 minus t. Okay, now I've reduced each polynomial to a product of prime factors, and now I can go ahead and cancel out the common factors or the opposite factors, as the case may be. T's are common factors of this product chain, so I'll cancel them out immediately. And t minus 3 and 3 minus t are opposite factors, so I can cancel those out, but don't forget to throw in a factor of -1, either in the numerator or denominator, that's fine. So I claim my numerator is equivalent to -1 times t minus 2 over downstairs 3 plus t. And that's a fine final answer. If you want to change how it looks in equivalent form, I could take that -1 and multiply it through in the numerator, and I get minus t plus 2 over 3 plus t, and that's a fine answer. I could absorb that negative sign outside the division process, and that's fine too. Don't forget that negative sign out here if you're going to do that. And I could even say this is 2 minus t over 3 plus t. Again, addition is commutative, so as long as you tag that negative sign on the t in the numerator, I can rearrange that order of addition. And again, any of these three answers are equivalent and would be acceptable. Alright, I think you get the idea, and we're approaching the 30-minute point, so we'll call it a day for section 6.1, Simplifying Rational Expressions.